Hello friends, welcome you all. So in this video, we are going to discuss one very important topic of theory of computation, which is halting problem. And in this particular lecture, we will discuss halting problem with the detail. So first we will discuss what is halting problem. We will define it formally. Then we will prove it and that it is undecidable problem. So let's define the problem, halting problem first. Halting problem is not a problem. Basically, it is a question. For any given program and a particular input, if can we decide that this program will halt for this particular input or not, or will it run forever, or will it trap in infinite loop. So this is the question. This is the question. So we will define it formally. So this is the statement of halting problem. Given a program and input, can we determine whether this program will halt or run forever? So this is the statement, and as I told you that halting problem is not a problem, basically it is a question. So this is the question. For any given program and input, can we say that this program will halt for this input or not? So this cannot be predicted, and it is very famous, and it is very famous undecidable problem. Now we come to decidability and undecidability. So what do you mean by decidable problem and undecidable problems? Now consider this program as one Turing machine, and consider this input as one string on the tape. Now for that particular string, that Turing machine will halt or not. This is the question of halting problem. And if for a particular problem, we can define a Turing machine that will halt always for all inputs, then we can consider that problem as decidable problem. If for any problem we cannot design such Turing machine that will halt always for all input, then such problems are known as undecidable problem. So in this way, we can define the decidable problem and undecidable problem. And why this halting problem is this much important? Because it helps us to determine the limit of computation. The limit of computation with the help of halting problem, or you can say with an example of halting problem, we can determine the limit of computation. And undecidable problems are the problems that cannot be solved with computers or machines. So all decidable problems we can solve with computers or machine, but all undecidable problems cannot be solved with the use of computers. So these two are different classes of problems, or you can say these two are different types of problem or different family of problems. So I hope you would have made some uh, base for the halting problem. Now we will define this halting problem formally, and we will prove that this problem is undecidable problem. So formally we can define halting problem as: consider one in machine as M. You can consider this as Turing machine, and one input to this as W. Then one machine that always halt, or in short you can call it as H, is for M comma W. This means M halts on W. So this is the formal definition of halting problem. And if H M W equal to yes, then it means it specifies M halts on W. If H M W is no, then it means M does not halt on W. So this is the formal definition of halting problem. Now, next we will discuss how to prove this problem as undecidable problem. So friends, we will use method of contradiction to prove this problem as undecidable problem. So I hope this formal definition and basic statement of halting problem would be very much clear now. Now we will prove this halting problem as undecidable problem. So as I told you friends, we will use method of contradiction to prove this problem as undecidable problem. Undecidable problem means no Turing machine exists for this particular problem. And if halting problem is undecidable problem, that means no Turing machine can predict perfectly that and for any particular input the machine will halt or not. Now, as we are using method of contradiction to prove this, so we will assume that such machine always exists. So assume HMW exists. Now this is our assumption that we are considering as base. Now let's define a Turing machine D. Let's define a Turing machine D which calls this halt D for any machine M which calls H M comma M. This Turing machine D calls this particular halting statement or assumption with M as an input, machine itself as an input. So as I told you, this D calls this function H with argument as with input as machine itself. So basically this D is taking input as M, this input as M. So you can mention it like this. Now when HM, if HMM says equal to yes, then D loops forever. It is trapped in infinite loop. And if H says no, then D stops immediately. Now this particular Turing machine D takes input as M, which calls internally halt M on input M. So if this says yes, so it D loops forever. And if it says no, then D stops immediately. So this we have defined. This we have defined. Now we will run this D on D input itself. So now after defining this Turing machine, we will run this Turing machine on input as a D. So I will call D as input as a D itself. So now if we are running this machine D as input, then if HDD says yes, then it's, what does it mean? It loops forever. And if HDD is equal to no, then it stops. That means on yes, it must halt, but it is giving as it loops forever. On no, it must stop. Sorry, it must run forever, but it is stops. It stops on no. That means whatever we are assuming, it is acting in opposite. It is acting opposite. So here it must stop, so it is running forever. Here it must run forever, so it is getting stopped. So this means both the time we are getting contradiction of what we have assumed. So at both places we have here it must stop, so it is running infinite times, and this is contradiction to what we have assumed. Here also it must stop, sorry, it must run forever, but it is getting stopped. So here also it is contradiction what we have assumed, and as it is showing the opposite behavior what we have assumed, that means whatever we have assumed, it is not true. It is not true. So we have assumed solution for a halting problem exists. So as we are having contradictory result in both the cases, that means this doesn't exist. This doesn't exist. So we can, with the help of this, we can write H M W doesn't exist. Now, if this is not existing, it means it is not decidable problem. And if it is not decidable problem, then it is undecidable problem. That means halting problem HMW is undecidable problem. So hence we can prove it that halting problem is undecidable problem. Now the last point is why it is this much important. So now, as I told you earlier also, it provides the basis for finding out the limit of computation. Limit of computation, that means we can find out the limitations of computing capabilities of machine. Second, one more important thing, it provides the basis for other undecidable problem, and it uh, to prove them as undecidable or decidable problem. So this is all about halting problem. So I hope this would be very much clear. Now, if you have any doubt, you can always write to me in comments. I will definitely reply our comments. Thank you. Thank you so much.